Okay, students, prepare yourselves for the third case in which the normal force is not going to be equal to the weight. Okay? Normal force not equal to the weight. We've had a couple of examples of this already, right? This is the third case. The first case was the elevator case, when you're accelerating up or down in an elevator. The second case was dragging the suitcase across the floor situation. In that case, normal force was not equal to mj, or mg for that matter. Third case here. Now, prepare yourselves because this is a little different. This has, in the past, maybe not this year, but in the past, this has created some conceptual problems for students. We're going to deal with a sled person taking a toboggan, which is apparently another name for sled up north. They call it a toboggan, apparently, going down a hill. All right? I thought a toboggan was a hat. I get confused. Anyway, in the past, up till now, we have dealt with situations where our axes looked like this. X was to the right and Y was straight up. Right? Looks familiar. But there's no reason to insist on such a set of axes. In this case, we're not going to use this. We're going to use X and Y. Don't get me wrong. We're not in some other seventh dimension somewhere. We're still going to use X and Y. But as I have said before, and as is eternally true, this choice of orientation of axis is arbitrary, meaning we could have chosen it otherwise. In this case, with motion on a so-called inclined plane, we're going to choose otherwise. We're going to keep the same old XY axis, but we're going to rotate it so that it's along the hill, along the so-called inclined plane. This is our first example of an inclined plane problem. We will see others, I assure you, but this is just the first one. Okay. We're going to rotate our axes so that Y is perpendicular to the inclined plane and X points straight down the inclined plane. In other words, we're taking our axis and rotating it through an angle theta. Same theta as the angle of the inclined plane. Pointing it down just a little bit. Okay. Now the reasons for doing this will not be immediately evident. There are, I promise you, if you can trust me, trust your physics teacher when he tells you that there are really good reasons for doing this. Maybe after doing a few of these problems, you'll come to see it for yourself, but for now, trust me, as we move on, I will point out exactly what troubles we would get into if we did not rotate our axis so it pointed down the inclined plane. Okay, so X is no longer directly to the right. X is going, positive X is downhill. Positive Y is perpendicular to the hill up in that direction. Okay? So here's what we got. Let's see. We know that the incline is, the angle is 22 degrees. Okay? And we also know that the slope, say it's like ice, whatever, and you got like an oiled up sled here. So we're going to be dealing with a frictionless surface. The question is, given that angle, given the fact that the slope is frictionless, the inclined plane is frictionless, we want to know what the acceleration is. Not the velocity, the acceleration. All right, so that's the problem. What's the acceleration equal to? Okay. Now, first step in such a problem is to draw a free body diagram, right? Number one, free body diagram. As I have said before with the previous two examples, first step, draw a free body diagram. So, what are the forces acting on this dude on the toboggan? Well, there's mg, right? There's the weight. We're assuming this is happening on the surface of the earth. I don't need to say that every time. It's happening on the surface of the earth, which means that the weight of dude is straight down. So mg, right? Weight is mg. That's one force acting on the dude. And we're taking the dude and the sled, together as a group. Okay. What's another force acting on the sled dude system here? What's another force acting? There's a normal force. There's a contact force between the sled and the hill. Just like right now, I'm standing here in the studio. There's a contact force up on me from the floor. We call that the normal force. So, the normal force, normal means what? What does normal mean? Not in contrast to odd or weird, but it means perpendicular. So the normal force here is perpendicular to the inclined plane, which means a normal force points off that direction. Okay, so we have two forces acting in two different directions. They're not opposite directions. They're not the same direction. They happen to be at this weird angle to each other. So those are our two forces. And I could have drawn a free body diagram down here by itself, isolated from the bigger picture. But I think in this case, I just drew it this way. You could do it either way. You could draw a separate free body diagram down here. But I'm going to do it this way to help you visualize what's happening. Okay, so the normal force is perpendicular to the surface. Okay. So I am going to draw now down here for the sake of visualizing what's going on. I'm going to draw our x here and our y here. There's our y. There's our x. Here's our normal force. A normal force is in what direction? Positive y. It's in the positive y direction. It's this way. So I'm now redrawing this to make it sort of as a teaching tool here. I'm redrawing this thing. You can redraw it again if you want to. When you work the problem, fine. And mg is straight down this way. And I'll call it mg as often as I'll call it weight. It's just that it's easiest just to always plug in mg for weight. Okay, that's the first thing. There's our free body diagram. Almost. I want you to remember what the second step is. The second step is apply Newton's second law. That's the second step. But you remember that we're dealing here in two dimensions, x and y. So that means applying two equations. We're going to have to sum the forces in the x direction, set them equal to max. And we're going to have to sum the forces independently in the y direction, set those equal to may. In other words, to complete, we're still down here. I'm just looking forward to remind you of what's coming and what we need this diagram to do. What we need from this diagram is to show all the forces in the x and y directions. Right now, the normal force is nice and clean in the y direction. Very simple. But mg is not along either axis. There's no way we can orient our axis so that both forces lie along x or y. Okay. Whatever axis we pick, one of these two forces, or both of them, is going to be off the x and y axes. The way we've chosen it, mg is off the x and y axes. So we have to resolve mg into its vector components. Let me draw this down here. There are two. There's the x and the y. Okay. Now in this case, I'm going to skip the explanation, okay, because that would take about half of the time for a video. I'm going to skip the explanation, but for now, I'm going to tell you that this is the angle theta. And we're not going to use the position angle in this case. Remember what the position angle is. That's the angle as measured from the positive x-axis. We are not using the position angle here. We want to keep things in terms of that theta. And this theta here is equal to, let me erase this here. Stick this in here. Make it blue. That's the same theta in both cases, okay? And so we have an x component here, down the hill. We have the y component here. And if you use this angle, not the position angle, ding, 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 not the position angle, but this angle here, then the angle in the x, then the component in the x direction is mg sine of theta. The component of the weight downhill is always, forever and ever, amen, mg sine theta, if theta is the angle of incline. The angle here is the component here is mg cosine of theta. And again, the reason why the x is sine this time and the y is cosine is because we're not using the position angle. Okay? We're using that angle right there and using that triangle right there. So mg sine theta points downhill, mg cosine theta points against the normal force. Now we have resolved our weight vector in the two directions, x and y, and we can apply Newton's second law. Let's do that. What are the forces in the x direction? Some of the forces in the x direction, actually let me do this way. We'll do y in just a minute. It's a little confusing to have the y sitting there. We'll do y in just a second. Some of the forces in the x direction. Let's look at our free body diagram here, right here, and ask ourselves which forces are in the x direction. Well, there's only one, and it's mg sine theta. Right, pointing downhill. Okay. And that equals m a sub x. Okay. Now let's apply in the y direction. By the way, yes, we're going to find the acceleration. Okay. I haven't forgotten what the original question is here. It is, what's the acceleration? We'll come back to that. We're getting there. We might go a minute or two over for this particular video. It's a little more going on here with the incline. We know that some of the forces in the y direction is m a y. Oh, I meant to put this here. Some of the forces, mg sine theta. What is the sum of the forces in the y direction? Well, how many do we have? Let's look at our free body diagram. It will tell us. And look at it. We got two forces in the y direction. One up, one down. Normal force is positive minus mg cosine theta equals m a y. So we have now taken the second step in our problem-solving strategy. We drew our free body diagram. Check. We have applied Newton's second law. Check. And the third step is to solve for the quantity of interest. Which in this case is A. Actually, I'm looking for, vector. A is a vector, right? So maybe I should put that right there. Okay, so this is going to go a little bit long. Okay. So let's look at our equations. How are we going to find A from this? Well, let's take this one dimension at a time. Okay. We're trying to solve for A, right? Well, A's got two parts, AX and AY. But we have oriented the axis so that one of these two A's, either AX or AY, is equal to 0. Which one's equal to 0? AX or AY? AY is equal to 0. It's not moving in the Y direction. It's not moving along the Y axis. We have changed our axes so that all of the motion occurs along X and not Y. So this is 0. And AX is our entire A. So all we need to do is to solve the first equation for A. I'll bring this down. Oops. I'll bring this down. mg sine theta equals ma. So we can solve this for A. We can actually cancel m's because m's show up on both sides. So A equals g sine theta. You know what g is, you know what theta is. 3.67 meters per second. Actually 3.7. Okay, because I only have two significant figures there for the angle. So 3.7 meters per second in the x direction. So there is our answer. A is 3.7 meters per second squared in the x direction, which is downhill, because we orient our axis that way. Okay. One more thing I want to say, get us up to the 18-minute mark here with this one. As advertised, the normal force is not equal to mg. Notice that if we solve the y equation for n, we get n is mg, not mg, but mg cosine of theta. N is reduced from mg. It's smaller than mg, okay, which is not equal to the weight. So this is the third case in which the normal force and the weight were not necessary. Notice also that I never ever gave you what the mass was. The mass is canceled right here. So it didn't matter what the mass was. The answer did not depend on mass. Answer depended only on the angle theta. A is g sine theta. All right, so that might be a record long video. I hope you stuck with it. It's important. We'll come back to other examples of inclined planes. Next up, Chapter 6.